Everyone to another OCP Tap session. This is call number 89. So today we have Stefan Maier. Stefan studied electrical and computer engineering at the Technical University of Munich, Germany, and University of Arizona. Received diploma engineering, which is equivalent to M.Sc. from Munich in 2011. And work for Rohde and Schwarz on E911 color location, A-GNSS. I think this is assisted GNSS, right? Assisted GNSS.
Yes, yeah, right.
Mm-hmm. Hybrid positioning engine, LTE and GNSS, and co-author of the book Location-Based Service in Cellular Network from GSM to 5G. And so today's talk is about 5G-based PNT using TV transmitters. So with no further ado, Stefan, the floor is yours.
Thanks, Ahmad, and thanks for inviting me and having me here in your group of timing experts. So I'm excited to present our project that actually started as a coffee kitchen idea and made it into a co-funded project, co-funded by European Space Agency. And yeah, we did several lab steps and even a live test in Vienna. And I'm glad to present you what we did. And of course, I'm curious about your feedback at the end of the session and the Q&A.
Wonderful.
Okay, great. Let me start with the problem that we saw. I mean, the problem is maybe that GNSS is too good. It's kind of the gold standard for so many timing users around the world. Everyone that needs some sub-microsecond time source, but even for the others that need a less accurate time source, GNSS is the way to go. So we use a GNSS receiver in our PTP masters. GNSS is free of charge. The receivers are very affordable. It offers a decent accuracy. And yeah, therefore, everyone loves to use it. And very few people actually have a different link. I mean, there may be some special customers that have a link with a fiber using PTP from NIST or PDB or USNO, but that's kind of the exceptional exception. The vast majority of users get the time usually from GNSS systems. So I kind of draw it here. There is kind of the ideal UTC, and then there are realizations from USNO, NIST, PDB in Germany, and the USNO is distributing its time via the GPS system to many users around the world. And of course, in Europe, Galileo system is doing something similar. But this is actually how most of us actually get their accurate time. Now, the problem is obvious. What if GNSS is not available for some reason or the others? You may say, okay, we have many GNSS systems at the same time, but they're all subject to the same failure modes. So if you have a solar storm, things like that, jamming, spoofing, they're all on the same L band. They can be knocked out at the same time. So if you're one of the lucky few that have a direct link to NIST or PDB, then of course you don't have a problem, or if you run your own atomic clock ensemble. But most of us don't have that luxury. So, or for example, if you're in motion, you don't have a wired connection anyhow. So what else can we do? So let's take a look at the RF signals that are out there and which ones we could actually use as a timing source. So here I just draw the signals that are openly available. There are some commercial sources as well, but this is actually what you can receive free of charge. As a reference, I added GNSS here. So GNSS gives us a few nanosecond accuracies depending on your receiver and on the GNSS system. And then there's of course the long wave systems, DCF77 in Europe, WWVB in US, and many countries have that. In Japan, there is also a similar system. Those systems typically operate on the long wave, low frequency edge. That means you have a very, very narrow bandwidth, and typically you get a few microseconds in the best case. Most cheaper receivers like a wristwatch, wristwatch RF receiver is probably more in the tens of microseconds at best. So this is what we get here. Maybe that's already sufficient for your application, but what if you want to have a performance more similar to GNSS? Let's take a look at other systems. There are broadcast systems like FM, RDS. I read some papers. I didn't do measurements myself, but it was written that it's more in the 100 millisecond range. So this is okay if you use it as for your radio alarm or for the clock in your car, but not for high-end applications. Let's take a look at terrestrial television, DVB-T2. The PHY itself is usually synchronized, at least if you have single frequency networks. So you can use digital television in two modes. One is that every transmitter operates on a different frequency on its own, or you combine multiple transmitters, they all send the same signal, they run on the same frequency, but that only works if they are somehow synchronized. But somehow means only to a few microseconds. So the goal here for those transmitters is usually less than 1 microsecond, 0.3 microseconds on the PHY layer. But the problem is this is not necessarily UTC traceable. You have a frame alignment, but you don't have any idea to which UTC time that frame actually matches. So those systems, DVB-T2, for example, also carries a time information, UTC time, in its payload, but this is like NTP or even worse. It's actually, this time is injected in the TV media stream in the TV station, and then it's transmitted to the transmitters, and you have any sort of delays. So this is in no way an accurate time source. Another source could be cellular 5G networks, especially if you look at 5G in TDD mode. You have those two different modes, FDD and TDD. In FDD, you use one frequency for the downlink and another one for the uplink. In that case, the base stations don't have to be very precisely synchronized. But if you use TDD mode, there is a mandate that all the operators have to sync their TDD transmissions to the UTC seconds. Otherwise, they would interfere with each other. So there is a requirement that you need to have your 5G network approximately 1.5 microseconds versus UTC in sync. In practice, that's even exceeded in some cases. Some operators also distribute the time there over fiber using PTP, so they reach better numbers. But in many cases, the base stations, the G node Bs, are actually also using a GNSS receiver. So you cannot really call it a backup system if it's itself dependent on the GNSS. And another thing is also that sending the broadcasts, this UTC information, broadcasting that is an optional feature. And many operators choose not to broadcast it because there's simply no demand for that and no one's paying for that, and rather use that capacity for sending data. So even if the base station might know the UTC, it's maybe not sending it to its users. And one thing is also, if you want to blanket a whole country like Germany, which is not a big country, you need more than 10,000 base stations. In the US or in China, it's many more. And it's also difficult to make sure that all of those base stations are all the time bringing you a correct signal if you want to use that really as a reliable time source. So what could we do if we want to get sub-microsecond accuracies? Maybe let's take a second look at the digital television. Why is it actually currently not usable as a time source? And what would need to be done to make it usable as a time source? So on the paper, it actually has a lot of nice properties to make it a decent time source. I mean, it can technically be, it could be built GNSS-independent. It's a terrestrial system, so it's not affected that much by solar storms. It has massive power. So a TV tower usually transmit at 100 kilowatt ERP in most of the world. In the US, it can be even 1000 kilowatt ERP, equivalent radiated power. So this is really massive compared to any GNSS signal. You can receive it easily also indoors. It's not that easy to jam because of that. The frequency is also relatively low compared to GNSS. It's in the 450 to 700 megahertz band. That gives you a decent indoor penetration. Transmitters have a very high availability. People tend to complain if there is an outage during a soccer match or stuff like that. And for that sake, many of those transmitters even have electricity backups. So they are very highly available. And the infrastructure is already in place, so you don't have to pay for that extra. The bandwidth is also reasonable. It's not like massive, but it's 6 to 8 megahertz per channel, depending on the region. In the US, it's 6. In Europe, it's 8. And I think in some places, it's 7. But it's some bandwidth that is kind of, in a way, similar to L1 commercial receivers. If you have a low-end L1 receiver, then that one is most likely also not using much more bandwidth than we have here. And still, it's giving us a decent accuracy. And the number of towers that you need to cover a country like Germany is only around 100 and not like 10,000. So if you would have such a system in place, it wouldn't be that hard to monitor it and synchronizing it. It's much easier than doing that for a cellular network. And one nice benefit is also you get very cheap directional antennas. So if you want to synchronize your data center to that TV tower, you can buy a Yagi antenna for 100 euros or something in your TV shop. So it's very simple, and then it's even harder to jam. So what is the problem? There are actually 3 challenges that we identified. One thing is actually the lack of receivers. So if you want to build a timing signal, you should also make sure that you get affordable receivers for that signal. And there is not a single digital TV standard. There are actually multiple. It's not like LTE that is used all over the world, but there's a European, there is an Asian, there is a American. So there are multiple different standards, and some of them lack this lower layer UTC timestamp, as I mentioned in DVB-T2, at least to my knowledge. Please correct me if I'm wrong here. But not all of these standards already have that timestamp. And of course, we want to have something not proprietary because we want to have that a lot of receivers someday hit the market and economies of scales kick in and you get decently priced receivers. So we have to think about the signal that we actually use for that system. The other thing is, can we improve the accuracy? I mentioned this 0.3 microsecond accuracy on the phi. Maybe we can drive that even beyond that, because 0.3 microsecond is probably something that you're not very excited about in the timing community, but maybe we can do better. And finally, of course, you have to synchronize all the TV transmitters in a way that is GNSS independent. It doesn't make sense to run those TV transmitters with GNSS receivers in turn. So they're not really a backup system. So I couldn't resist. I was creating some artwork from DALL-E for my stuff. So I used some of the artificial intelligence images. I couldn't resist trying that out today. But let's first take a look at the signal itself. So there are actually 4 global digital television standards. There is ATSC 3.0 in North America. There is DVB-T2 in Europe, Africa, and many places of Asia and Australia, Oceanic. There is ISDBT, which is used in Japan, also in South America, and some places in Africa. And then there is DTMB, which is used in China and some of the neighboring countries. So there is not a global standard, as I mentioned. So which one should we use for our project? So we actually choose to use yet another one, which is not used anywhere else, but there's a reason for that in the next slides. But my message is actually, you could do that with any of those standards, to my knowledge. I think there is nothing preventing us of using or getting the same accuracy with a different standard. There's, in fact, a project or a team that is trying the same thing with ATSC 3.0. We noticed that after we already started with our project, they're actually going in a similar direction. They want to use ATSC 3.0 as a time source. But I mean, the TV transmitters are essentially software-defined radios, so you can adapt them to any of those. We choose this 3GPP FEMBMS, which sounds pretty awkward, but in essence, it's not something very strange. It's actually LTE slightly adapted for broadcasting from TV towers. So it's the good old LTE signal that we have in our phones. The standard comes from 3GPP, which is the standardization body that also designed 4G and 5G. So it's essentially some sort of LTE signal. And being a LTE signal, we can take advantage of all the positioning features that are there in 3GPP. So I call it here the toolbox. For example, there is a UTC timestamp that we can use in 4G signals, and we can use the same thing in our broadcast signal. There is also a method for transmitting the location of the transmitter. So there are some things that we can actually reuse, and we don't have to modify the standard or anything. We can just use the standard as it is. And I mean, there are a lot of LTE modems around there, and this FEMBMS would actually work with a small software adaptation. So you don't have to touch the modem hardware, the silicon. It's actually a software modification for a modem to make it a FEMBMS receiver. When you click on the link here, my colleague is actually showing some demonstration where he's showing a commercial phone. The hardware is commercial, the software is patched, however. So you cannot buy it like that, but it's only the software that is patched, and that phone can receive a TV signal from a cell tower, not from a cell tower, but from a TV tower, and display a video stream. Not a timing signal, but it's actually internally also decoding the UTC time for that purpose. So it's actually possible turning a LTE modem with some software modifications into a receiver for that system. So this is why one reason why we choose it. So it offers a path to low-cost timing receivers. Here are some differences. I don't want to go into the details, but one thing is our signal from the TV stations doesn't have an uplink, obviously. So it's intended as a downlink only signal, and you can design it or you can configure it differently or more similar to LTE. We choose a setting that was fairly similar to LTE. But in both cases, you can send the UTC time via the very same method and also the transmitter location. However, there's a small gap in the standard. For some reason, they didn't add it that you can send the POSIPs that I mentioned later on, which is carrying the transmitter location in the TV variant of LTE, but that could be added with a small addition. So it's not a big deal in the standard. So how does the LTE signal look like? Probably most of you are familiar with that. This is a LTE resource grid. The x-axis is the time and the y-axis is the frequency. So every row here is actually a subcarrier and every column is an OFDM symbol. And you can see here, there are a lot of pilot signals inside the LTE. So there is the primary synchronization signal. This is the green one. Then there is the secondary synchronization signal, the yellow one. You can already use those two to identify the frame start. And then there are also cell-specific reference signal that additionally help the receiver. So basically the steps to decode a UTC time from an LTE or FE and BMS signal is that first your receiver has to log on the PSS, primary synchronization, secondary synchronization, read the cell-specific reference signals, and then it can actually read the master information block, which carries fundamental data about the cell, like the bandwidth, and then it can decode the system information block 1, SIP1, which comes always in subframe 5. And the SIP1 is kind of a container that tells us only where to find other system information blocks. System information block is kind of the broadcast channel of LTE. And so the SIP16, which is actually carrying the UTC time that we are interested in, could be anywhere here in the grid, but we learn where it is from the SIP1 that we can find here in subframe 5. So this is actually just the standard way how you actually acquire a LTE signal, nothing special about that. And reading SIPs is a standard procedure. I mean, your mobile phone is doing that all the time because it needs to read that information for the attach, for the handovers, and things like that. Well, now that we know how to get to the SIP16, let's take a look at what is inside the SIP16. The SIP16 is actually specified in 36311 if you want to read it up. That's publicly available specifications. And this contains a time info element, basically time info UTC, which is the number of 10 millisecond units since the beginning of the last century. And it also gives us the leap seconds. So with those two together, we can actually calculate the UTC time, the GPS time, anything you like. And this also says, okay, this is exactly, this value is valid at the SFN boundary, which is basically the frame start at a certain moment. So it's very well defined when this UTC time is applicable. So you can use that very nicely to as a time source. What about the transmitter location? So if you don't know from a map where your transmitter is, you may want to learn that from the signal as well. And just like in GNSS, you can do that here as well. The transmitter is carrying its own location, or it can carry its own location in the so-called POSIP. It's just a different type. It's not SIP16. It could also be called SIP35, but for some reason they called it POSIP. So this is actually how you can learn the TX location. And the TX location is a latitude, longitude, altitude of the antenna phase center. And it can even contain a beam info, which is probably not very useful on UHF bands because the beam is very broad. That's more something for the high frequencies, but it would be there. But basically, the most important thing is we can learn the transmitter latitude, longitude, altitude, and then you can compensate for the signal travel time, for example. So this is actually what we did. We were implementing this LTE standard for our TV transmitter. Maybe I haven't mentioned it yet, but RNS is not only building test equipment, but also TV transmitters. So the Coffee Kitchen idea was actually to integrate that in our TV transmitters. And our TV transmitters are now updatable via software to emit such an LTE signal that carries the UTC and the SIP16. And it also carries some more stuff like the position information and a positioning reference signal that is less important for timing, but could be used if you want to measure the time difference between multiple transmitters. That becomes interesting if you want to use that for location, not only for timing, but for the N in PNT. Well, this is actually what we did as part of the project. We kind of added those elements, and we needed a receiver. So the mobile that I showed you before was able to decode the video stream and also the UTC timestamp, but it was only using it internally. We couldn't get access to that. Therefore, we used a measurement receiver from RNS, which is normally used for doing coverage mapping of a cellular network. So you drive around with a car and connect it to an antenna so that you see how good the mobile network coverage is. But this guy can actually give us a pretty nice PPS out time for the frame start. So we can use that very accurately to measure our frame start. So this could be used as a timing receiver in essence. And from what we tested in the lab, it should be around 50 nanosecond accurate. So this is actually the error that is introduced by the receiver. We also did some experiments with an open source Lime SDR, but at least I didn't find a way how to get a PPS out from that thing. So you can try to decode the signal, that is all working, but getting the time out of that box is maybe a different story. So we mainly did our tests with that RNS device. So with that equipped, we had a receiver, we had a signal implemented on the transmitter. We could actually look at the second thing, the accuracy. So we wanted to see what we can do with the accuracy. We didn't just want to use the transmitter as it is. We wanted to see, can we drive that a little bit further? Because the TV transmitters had a design goal for the engineering department that was maybe 1 microsecond, and they already exceeded that, being 0.3 microsecond accurate. But that is more than enough for a TV signal, but for timing, we wanted to see, can we do better by doing only software updates to the transmitter without modifying the hardware itself? Of course, you can do better if you redesign the hardware from scratch, but we wanted to see, is it possible to create a software update that you could just patch on those transmitters that are used all around the world in many, many TV stations and make them more accurate. So for that sake, we actually built a rack with 3 TV transmitters and a PC connected to this TSME receiver that I just showed you. There were no amplifiers. That's why it's only 1 rack. So it was only a few milliwatts that we tested, of course, but that was sufficient to analyze the jitter that was introduced by the TV transmitter itself. So the TV transmitter, this is actually a high-level picture of our TV transmitter. The TV transmitter has a PPS in already, and the PPS in is then used in an OCXO control loop to steer an internal OCXO. So the idea is actually it's not directly using a 10 megahertz signal, but it's just using the PPS. And if the PPS is failing, then the OCXO can still bridge the gap to continue transmitting the TV signal for quite some time. The OCXO in turn is actually delivering that frequency, and that is used in the FPGAs, DSPs, digital analog converters. So this frequency stability is massively influencing the RF signal jitter that we get in the end. So we fed in the PPS from a rubidium clock. We fed in the same PPS into our test receiver, and then we did the analysis, how much does our RF signal jitter versus the PPS in that we hand over to our transmitter. And at the same time, we looked with an oscilloscope at this frequency that was generated by the OCXO. We wanted to see what was happening inside and what is coming out of the TV transmitter. And doing that, we ended up with this plot. Actually, this is a magnified plot. So you have a number of PPS triggers, so 10 to the 4 PPS triggers, so 10 to the 4 seconds. And here you have the jitter that we saw. So when did the frame start happen after the PPS? And this was, as you can see, jittering quite significantly. There were some zigzag pattern, kind of some systematic issue, obviously, and there were also some jumps. And in general, however, it was following this red curve. So the blue one is the RF signal, the measured RF signal versus the PPS, and the red one is the frequency drift of the internal frequency. And you can see there is some connection between the frequency. The internal frequency was also going up and down. You can see this control loop was pretty relaxed. It didn't act quite quickly. And this was why the signal was all in all going from minus, don't know, 80 nanoseconds to plus 200 nanoseconds from the average. So we had more or less 300 nanoseconds, 0.3 microsecond jitter in the signal. So what can we do to make it better? Obviously, there were two control loops in the transmitter, the OCXO control loop and another SFN regulator. It's also a control loop that is supposed to synchronize two TV transmitters if they run in SFN mode. And as said, I mean, this doesn't look good, but it's more than good enough for TV transmission. But we wanted to drive that further. So what we did first was actually we bypassed the OCXO and fed in the 10 megahertz signal from our rubidium clock. And then the signal looked already much better. There was still a systematic offset or systematic effect. But if you removed that very systematic effect, then the residuals was only 50 nanoseconds. So that really encouraged us. So we thought, okay, if we sort out the problems, then maybe we can end up at 50 nanosecond jitter contribution. Of course, we didn't want to do that in the field. We didn't want to put rubidium clocks in all the transmitters. It should stay with the 1 PPS input. So we looked at the OCXO control loop and the SFN control loop. And then after several iterations, we step by step improved the signal, and we ended up here at a signal. This is, again, without hardware modification, just by software updates, we got a signal that is peak-to-peak 40 nanoseconds versus the PPS in. So this was actually, we were quite happy with that. I'm not saying that this is the end of the optimization. You could probably still do better, especially if you think about a new transmitter generation where the hardware is developed from scratch. You can probably push that significantly below those 40 nanoseconds. But this is what you can do with existing transmitters just by software updates. So give you the scale, actually, we came from here and we ended up here at the 40 nanoseconds. And this was what kind of we used also in the field tests that we're following. So we didn't only want to test it in the lab, we also wanted to see how it's performing, especially with a focus on positioning. So our focus in that project was more on positioning than on timing, but I think you can derive the timing accuracies from the position in the end. So what we were doing here, we were cooperating with the Austrian broadcasting company ORS. So they were kind enough to let us test our signal from 3 of their transmitters. So we got access to that on the skyscraper, on the mountain, and a smaller one. And those 3 transmitters were more or less around downtown Vienna. And then we did some drive tests. We connected a GNSS receiver and our receiver, and we drove around with a van in downtown Vienna. And you can see the red one is the ground truth from a multi-GNSS receiver. And all these small dots here are individual position calculations. So we didn't do any Kalman filtering, but we used individual position calculations. So the figures of those transmitters were already pretty large, but not the highest power that you could get. So 40 kilowatt from this one and 10 kilowatt from the 2 other ones. UHF band means 666 megahertz. That was the test frequency. And we used a bandwidth of only 5 megahertz. So we didn't even use the maximum bandwidth because of limitations of the test frequency. So here is a magnification of an area where it worked quite well. So here you can see the red line where we drove, and then all these green dots are actually individual position calculations, not filtered. But of course, it's not as good as GNSS. I'm not saying that we can kind of replace GNSS, but it lets you guess quite well which street we took if you look even at only the green dots. And if you do some filtering, if you would do that, then probably it would look even better. But for timing application, what is more interesting than a drive test is probably the static test that we did here. This was really on a rooftop of a building that had line of sight to all 3 transmitters. And then we were doing time difference of arrival measurements and calculating the position. So what you see here is actually this whole green scatter plot is actually all the positions that we calculated over a time of 20 minutes. And we did that over several hours. And as you can see here, I mean, the 20-minute scatter is relatively small compared to the overall drift. So we see the slow drift over the 3 hours. And we did not see that in the lab. In the lab, we saw something that was more similar to the scatter plot over 20 minutes. So our suspicion is that in the field test, we were using GPS disciplined oscillators. So the transmitters were not precisely synced to a common clock, but they used GPS disciplined oscillators that were not super high end, but just good enough for television. So we think that this was the main reason why this whole scatter plot was actually drifting. But if you look at, if you think without that drift, we could have reached something like more in the 25 meters. And this is also what we saw in the lab. So actually we think that our transmitter introduces probably an error of approximately 30 meters, 25 meters. This is actually the error contribution that our transmitter and our receiver together bring actually. So yeah, here are some figures of the error distribution. This is actually the 20-minute subset, and you can see 95% of the measurements were within 24 meters. So I would say probably the accuracy that you could reach with that system is between the 40 nanosecond that we reached in the lab and maybe something like 80, 90 nanoseconds. So it's below 0.1 microsecond that you should be able to reach with such a system in the field. All right, let's take a look at the third chapter, network synchronization. So we have many towers that need to be somehow synchronized, ideally not with such a clockwork, but with something more state-of-the-art. So what could you do? This is actually the list of Germany, or the map of Germany, with all the TV transmitters. You can see all the blue dots and the white dots. The difference is only that in the blue dots, more stations are actually broadcast than in the white dots. And this is also the difference between the dark blue and the dark green and the light green. In the dark green, you receive 6 multiplexes. In the light green, you receive only 3. But even in the light green areas, you could actually use the system for time synchronization. So that wouldn't be a problem at all. So there are some gaps, as you can see here. And of course, there are some regional gaps. If you're in a rift of a valley, then you probably won't receive the signal. But you could get a pretty decent overall coverage of a country like Germany with a decent number of TV transmitters. So how are those TV transmitters actually getting their TV signals, we thought? So one thing is, historically, they had microwave links. And even today, in many cases, they still have microwave links. The reason is they're often in more remote areas, like on a mountaintop, where it's not so easy to get a fiber link. But they have those microwave links, and that's maybe not even a bad thing. Of course, if you have a fiber link, the easiest thing is actually to use PTP, maybe with White Rabbit. Probably you don't even need White Rabbit, but to use PTP to provide the PPS time to those transmitters. But those transmitters that have a microwave link can also be connected and synchronized quite easily. There are proprietary systems that offer even nanosecond level time sync over microwave links over large distances. What I don't know is actually if you go for regular PTP, or let's say IP-based microwave links. Some of them also offer PTP time transmission, but I didn't find much information about the accuracy of those commercial microwave systems that are based on Ethernet, for example. So it would also be possible to use that, but yeah, maybe there's feedback from the audience. I would be curious to learn what accuracies you can reach over a PTP connection over microwave. But if you choose the right system, if you're willing to use a proprietary system, for example, you could establish kind of I call it a timing backbone. You could connect all these TV transmitters, and the nice thing is they were all on large towers or tall towers, and in many cases they were historically designed to have line of sight contact to each other or to some intermediate relay station. So getting microwave links between all these TV towers is actually not a horribly complicated task. So you could actually say that you generate a microwave or fiber backhaul where all these TV towers would be provided with a precise UTC-traceable time. And then each TV tower could actually broadcast the TV signal to the end user. So the end user would then get a less accurate version of the time, but still in the sub 0.1 microsecond range. So way better than what you get today with DCF77. You could also say if you're a high-end user, I drew that in here as an example. You could also say I tap the backbone directly. So I could say there is a TV tower in Munich. I have my company, my data center somewhere near Munich. I spend the money for a specialized receiver, not the cheaper receiver. I get a specialized receiver, put a directive antenna and point it to the TV tower, and then I get my nanosecond level time instead of the 40, 80 nanosecond time for the average audience. So this, of course, is just hypothetical. This is not in place, this timing backhaul. It's just something that we were thinking could be a viable way to synchronize TV stations, to kind of make sure that they were synchronized without using, again, GNSS system. And if you do all that, then you would have a completely GNSS-independent second time source that you could actually integrate in your PTP master, and you would have a long time holdover backup system in case GNSS time would not be available. So this is actually a summary of what I wanted to present you. So to come back to that chain where we get our UTC time from, this would actually be another link in that mesh. So instead of just getting it from the GNSS systems, we could, for example, tap the NIST PTB to get time from a different clock ensemble and then distribute it to the PTP masters or even to the clients in the end. And that chain would actually be pretty independent of the GNSS chain. So you use a different atomic clock ensemble and you use a different distribution mechanism, which is also in different frequencies and also not in the orbit. So its failure modes are pretty different from the failure modes of a GNSS system. At the moment, as said, you can probably reach something like 40 nanoseconds, but this is really without spending much effort on the transmitters, just by software updating them. Of course, if people really say, okay, this would be useful, we could also think about a redesign of the hardware. And if you take that higher accuracy requirement into account from the beginning on of the designing of a TV transmitter, you can probably drive that number beyond the 40 nanoseconds quite easily. So where does it put us? So I put the TV signal actually here. It's actually worse than GNSS, but it's in a way more reliable than 5G cellular because you have less towers to monitor. So it would be actually kind of a gap filler for the timing users that want to have a time source independent of GNSS in the sub-microsecond range. If you have a cable, of course, you can take the time card. That's a perfect thing. And you can use PTP, PTP White Rabbit. But if you need to go over RF, or if you want to seed your PTP master, then TV signals could actually be a viable way of getting a second source and making the whole system more robust. Well, that's it so far. So for information, this activity was actually co-funded by European Space Agency under the NAV ISP Element 2 program. So part of the money was spent by RNS, part was spent by ESA. And you can also see the final presentation from that project. It's also publicly available, but it's actually containing similar information than what I showed you today. Okay, that's it from my side. So with that, I thank you for your attention and would like to hand over back to Ahmad.
Wonderful. Thank you very much, Stefan. All right, so let's open the floor for questions. Nobu, do you have a question? Go ahead.
Yes. So hi, Stefan. My name is Nobu, and I work for Japanese government lab called NICT, and we are in charge of Japan Standard Time. So it's sort of like a PTB or NIST equivalent of Japanese version for time and frequency standard. Anyway, so I have been working on the wireless synchronization. So I mean, I would like to discuss with you more. But you mentioned that you sort of thinking about the millimeter wave or microwave synchronization. And so my question is, do the TV stations, do they have the two-way communication capability?
So to my knowledge, usually the links are already bidirectional, the backhaul links.
Okay,
so
great.
You already have some bidirectional communication because, for example, in Germany, it's like the headquarter of the TV station is in Munich, but the transmitter is, for example, in the mountains, but they are remote controlling it. So they also want to get some data back and see, is the TV transmitter working operationally? And so it's usually a bidirectional microwave link that is already in place.
Oh, great. I mean, so my comment would be, if you already have the bidirectional communication, I mean, wireless communication, then I think you can do sub-nanosecond fairly easily with the synchronization and just doing the two-way synchronization. I don't go into too much detail, but I'm just mentioning that we know how to do it, so we can talk with you more.
That would be very interesting. Yeah, maybe I would be looking forward to follow up with you.
This is Ramki Ramakrishnan. I have done some work with two-way time transfer with satellite and microwave radios. The challenge with microwave radios is line of sight. Communication is multipath. If we can handle that, we have seen under 10 nanosecond synchronization accuracy. Of course, with SATR modem satellite, expensive, you can easily get to below 5 nanosecond accuracy, but those are very expensive options.
Mm-hmm. Yeah, that would be interesting. If our transmitter is adding 40 nanoseconds of jitter, then probably you don't have to make the backhaul for sub nanoseconds if you don't plan to distribute the signal elsewhere. But yeah, would be really interesting to see what is possible. And the nice thing is really, I learned, for example, in Germany, they built those TV towers for the Olympic Games also in 1972. And back then, the standard way of relaying TV signals was over microwave. So they have all these relay stations still in place. They are still existing. So you could, this link is probably not going from Munich all the way to Pfaffenhofen, but maybe there's a relay station in between, and those are still existing. So you could actually have line of sight links between all of those TV transmitters in many places, I think.
Ramki, I've thought, I have one comment about the reflection or line of sight. If it's for the time synchronization, the not having the line of sight or having reflection, it doesn't really matter as long as you are capable of communicating both ways, because the sort of the reflection or the non-line of sight, the propagation delay is canceled. So as long as going one way and the other have the same path, then it doesn't matter for the time synchronization is what we have been seeing though.
Okay. So basically, because of the two-way, you can do a round trip cancellation of the whatever happens.
That's right.
Yeah, no, I understand.
Yeah.
No, yeah, when we did this work, it's several years back, for a customer in Asia, we decided to not pursue that, and then we needed to go to the satellite route, but they wanted below a 5 nanosecond accuracy for a government customer. But yeah, I'm sure there's more improvement to technology, and obviously you have tested it now. You probably know what's going on. Thank you.
Well, I think one thing could also be that this backbone network could also be useful for other purposes. You could actually say from this backbone, you kind of, in Germany, the PTB is sitting somewhere here, I think. Braunschweig actually here. So if you want to get the time in Munich, it would be nice to have such a backbone in any case, even if you distribute the time then in Munich via fiber inside. But this backbone system could actually be serving multiple purposes, except only
Stefan,
providing the time to the TV towers.
Stefan, the other thing you may want to think about is how many people need below 30 or 40 nanosecond? Because if you're already doing 40 nanosecond, you're going to serve 98% of the applications in the market. And I have experience transferring time or a dedicated optical connection over 1,000 miles, a PTP Grandmaster connecting to a NIST type national lab, and then transferring time over a dedicated gigabit, 10 gigabit optical circuit and recover the time on the other end. I have typically seen below 100 nanosecond accuracy, and in many applications, based on my little experience, it serves most of the applications. So if you guys are already doing 40 nanoseconds, I think you can really serve many applications satisfactorily.
Mm-hmm. That would be great. Yeah, thanks for that feedback. So yeah, I think that's actually the target of this project, was not the super high-end side of the things, but kind of the average user that needs something a little bit better than DCF77 or this long wave signals. That was kind of the.
But yeah, I mean, I want to chime in about that, and yeah, but Stefan was talking about the localization, I mean, positioning as well. And if you go for positioning, I mean, you want to have, well, you want to go for sub-nanosecond, I mean, around nanosecond, right?
Yeah, I mean, what we were also investigating was actually, of course, you could do something like differential GNSS. You could establish monitoring stations that are sending corrections to those inside the signal. So then you can also improve the accuracy, maybe even without further changes on the hardware. Yeah, so that could be also a viable way, but I think, I mean, what we thought is actually, we just wanted to see how far we can push it with a software update, and also kind of to start it as a test balloon. If we get feedback from the community that they say, okay, it's useful, but we would need a little bit more accuracy or much more accuracy, then this could be something that could be further developed. It's not like the hardware itself could actually be made more precise, I think. But of course, that would be a development effort. But on the other hand, if there would be the response, okay, we don't need anything like that, then okay, we can also save that effort. So I'm curious about learning that feedback and hearing what it's actually useful. The other thing is also talking about positioning. Honestly speaking, we also started with that, and there are many places in Germany where you see more than one TV transmitter at a time. So they're actually overlapping quite well, but not everywhere. So we were estimating that maybe half of the places, half of the area of Germany, you see at least three transmitters, but in the other half, you don't see three. So for positioning, you probably need to densify your transmitter network. That would be possible, but it's probably not. I'm not saying that this would be immediately solving your positioning problem for terrestrial application. Okay, if you say that you have an airplane that you want to locate, then you're probably in a better position because you see more transmitters. But if you're on the ground, then you may need to densify your network for positioning, but for timing, it may already be sufficient in many countries.
But Stefan, if you cannot identify the position because you don't have multiple transmitters, then you need to know the distance to the transmitter in order to compensate for the transmission delay, right? So yes. You need to either go for bidirectional communication or find more than three transmitters in order to get the accurate time. Otherwise, you will suffer the offset.
Yes, yeah, you're right. For mobile application, that is certainly necessary. Yeah, for mobile application, if you have ground-based mobile application, then this would be necessary. What you could still do is, if you have a local holdover, if you have a chip scale atomic clock, then even two transmitters would be sufficient for some limited time to get your position. But of course, not endlessly. So you would need to occasionally see three transmitters to adjust that. But then you could actually probably live for quite some time with the internal clock with two transmitters, and then you can increase the number of, or the share of area that you could locate yourself. But one thing that we thought of is also maybe not so much mobile applications in the first step, maybe at a later step when the network is also densified. But in the first step, it would be static applications like a data center that is somewhere located. They could actually put up an antenna and they know anyhow where they are.
Thanks. Makes sense.
Yeah, thanks for the input.
Ahmad, you are muted.
Thank you, Nobu. Yeah, so another question with regards to Lime SDR. Like Lime SDR has the PPS input. I've seen it. Like I was playing with one in the morning. Like, what was the problem? Because I can get it back to Ibrahim and see what they can change in it. Would that be possible to have, let's say, something open source we can run on a Lime SDR to receive the PPS signal or something like?
Well, the software itself is open source. So the receiver that is doing all the decoding of the LTE signal, of the FE and BMS signal, actually, that is open source. That is actually developed by an Austrian partner company by the ORS. So that is actually what is called here OBECA. So if you Google for OBECA, you should find some Git repository where you can find the software.
Yes.
What, honestly speaking, after we had this PPS out here from this receiver, we mostly focused on that one. So that's interesting input that you could actually get some PPS in or PPS out here.
Yes.
That would be great. I would really encourage that if there's, we actually started with that one also. The idea was to use it as a Kickstarter. If there's a university project or students that want to play around with that system, then they could actually, they don't have to buy that one, but they could do something with that, and we would love to support them. And if they extend that software code to bring out a PPS out, perfect. That would be fantastic.
That's what I was thinking, because like it's good to have a lower bar to get started, and then let's say we can then figure out what we can do with it, like the applications, like how to basically go further with the time, like basically whatever this SDR delivers will be much easier when you have it more accessible. And then if something more advanced, then there are like basically all these commercial boxes that you're offering and so on.
Yeah, I think that would be fantastic. I would love to see that. I mean, if there is some academia or university or any group interested, also commercial group interested in working with that, just let me know, and we can maybe also try to provide you waveforms for testing and stuff like that.
For sure. Any other questions? I mean, another thing, you want to ask that question, Abu?
Well, I mean, I don't want to speak all the time, but I wanted to mention. So if you bring put the German map again, the one thing I wanted to mention is that there is one application for the microwave sort of mesh network or comparison network. And so if we have the bidirectional comparison, you can basically synchronize. And not only that, you can also measure the propagation time, which reflects the change of index of refraction in between the atmosphere. And so that index of refraction hugely depends on the amount of water vapor that contains. And at the moment, there aren't many ways to measure the surface atmosphere water vapor. So that is very useful for the weather prediction database. And so we have actually demonstrated that by doing that, you can actually, so suppose it's like 5 kilometers away, then within a day, you can see the distance looking like it changes like tens of centimeters with over 5 kilometers. So if it's like 10 times more, then you see much longer change. And so yeah, that's another application area. By having the synchronization mesh network, then you can gain the atmospheric water vapor monitoring for free almost.
That's interesting, yeah. And maybe as a second step, it may also be necessary to provide correction data. Like we have the ionospheric model for GNSS. It could also, once you have such a network, you could maybe also provide a water vapor correction data for that system.
This is, I think, related to a work like I saw in EFTF in Japan. I don't know like which university was involved with that. Do you remember that, Nobu? Like
I didn't go to EFTF, but NICT has been working on actually using the TV signal in Japan to monitor the water vapor in Japan. So we do that actually.
Yeah, there is an entire cloud for real, not cloud cloud model. And you can, I think they were using Leo, with different ground stations to find, let's say, again, water vapor in between. They had a model. I forgot. There were a lot of interesting details in that presentation. I probably can find it and put it back for everyone. All right. We have 3 more minutes left. Any more questions? No, don't be shy if you have another question.
Well, I talked to Stefan later. I mean, I'm pretty satisfied for now.
Any more questions? Hearing none, I can give you back 3 minutes.
Okay, thank you.
Thank you again, Stefan. And next talk will be by Microchip. David's gonna, I think, give the talk. Let's see. Yeah, David Chandler will give a talk on December 20th. All right. I heard something. Anyone wants to ask a question? Or
What's the topic?
it's about the role of quantum physics in primary time and frequency references.
Oh, wow. Very interesting. Thank you. I'll be there.
All right. See you guys in 2 weeks.
All right. Take care.
Bye,
Bye-bye.
everyone.
All right. Thanks for having me here. Have a good day.
Bye. Thanks.
Good night. Bye.
So Stefan, I'm sorry. Can
Yeah.
I? So what's the best way to get connected with you? Email, LinkedIn, Facebook?
You can connect me on LinkedIn, but I can also, I don't know, can I post something here in the chat? I can also put my email address. Okay. Yeah.
Yeah, thank you.
Probably email addresses.
Yeah.
Monitoring more closely.
I will try to get connected with via LinkedIn as well, but I will send out email. But thanks a lot for your interesting talk. It's
Yeah,
sort
thanks
of,
for your feedback and
yes,
questions. So I would be curious to say, so one question. So in Japan, you also have this long wave system, JJI.
yeah,
something.
JJY. Yeah,
That is also run by your institute.
that's right.
Or?
We do run
Okay.
it.
Okay, got it.
Okay.
Okay,
Yeah.
and you're also running the clock ensemble in Japan, like?
Yeah, we do. And
Okay.
we make atomic clocks, and we do wireless synchronization, and we do many things actually.
Okay. Yeah, that would be interesting, because that would be actually, yeah, our preferred partners. If you build such a network in Japan with the TV broadcasting companies, then it would be wonderful if you can get the time from an institute like yours.
Yeah, I haven't been successful about that yet. So that will be interesting to talk to you first, actually.
Okay, yeah, would be great.
Thank
Love to stay in
you.
contact. Okay, thanks for your time. See you. Bye.
Bye.